welcome to science class, sort of. If this was science class, I'd be an awfully absent-minded professor because we're going to cover all sorts of things. So I don't really intend for this to actually be a science class in the sense that I have a lesson planned for a specific lesson, but just I've got a bunch of different experiments and demonstrations that I thought were neat, and I want to share them with you and just talk about them. And maybe let's start though. Well, first of all, I'm Doug Kauffman. I know some of you. I teach school in Harrison, Arkansas. This is my 7th year of teaching, although it's my first year back in the classroom after about 10 years out. So it's good. I'm enjoying it again. I will say too that, well, let me hold that thought.
Are you looking for these?
Yes, thank you.
I think it's out of paper, so there's probably some more.
This is probably anyway.
Okay.
Thank you. So I do have more handouts here, and if y'all want to, any of you didn't get one, feel free to grab one, take them home. I tried to leave a little bit of room on the handouts for you to take some notes and jot stuff down. There's also a note page in your pre-made program that you can write stuff down. I just didn't have the handout ready to go in time to get it printed for the program. So. My first question, and I'd like to just open this up a little bit before we start into any of these demonstrations, is why even do science demonstrations in the first place? I mean, if you've got a good textbook, that should cover it, right? Good explanation. I mean, I think we kind of know some of the answer already, right? There's just doing stuff hands-on or seeing it done helps them make connections in our brain that just reading about it doesn't often do, right? That's true even for me as a teacher. I find that when I have to demonstrate something, or even just think through how to best demonstrate something, it helps me as a teacher to understand the concept better, and then I can help to explain it better to my students. I am not actually, I probably shouldn't have taken this course or this class because I'm really not a science guy. I shouldn't say that. I do enjoy it, and I really enjoy figuring out how the world works and how the wonderful intricacies of creation, how everything's put together so amazingly. I enjoy math kind of for the same reasons, but I'm more of a history, philosophy, language guy, probably, naturally. But I find that when I can do stuff like this, it just makes science come alive for me in a way that makes me really love science too. It's a little bit like when I was in, I took a college algebra class, an honors college algebra class, because I don't know, I didn't have a whole lot of high school algebra, but somehow I guess my test scores were, my college placement test scores were high enough that they said, oh, you go into the honors college algebra class. That was a mistake. Well, it didn't turn out to be a mistake, but I thought it was for the first little while. I was upper 20s at this point. I had been out of school for a while. I had been teaching school when I stopped teaching and went back to college. Actually to be a nurse, that's kind of another whole story. I've worked the last 6 years as a nurse. I guess I can't decide if I'm a teacher or a nurse. But in my college algebra class, I was in an honors class with a bunch of high school kids. I mean, just got out of high school, and they knew their stuff. And I didn't. I'm the old guy here that doesn't know what he's doing. But the reason that I actually got a good grade in the class was because the professor in that class didn't insist on me just memorizing formulas and memorizing stuff, but she did really good at explaining, did a great job at explaining concepts in a way that my brain could put it together, and she could demonstrate it. Obviously, algebra is a little different field than a lot of these physical sciences, but the concept, I think, is the same. That if all you do is go through the science book and expect your students to sort of memorize formulas and understand stuff by just knowing it, just putting it in there, it's not going to work. I would not have done well in that college algebra class if it wasn't for a teacher for whom it was more important to understand the concept and how to get to the end rather than doing the right steps all the way. Now, obviously, the right steps are important, especially in algebra, actually. But I think there's an analog there to science. And I mean, just let people figure it out and show them. And don't, it works a whole lot better than trying to just tell them. For sure. Do you have any, why do you do science demonstrations? Or maybe I should say why, well, maybe we should talk about why don't we? Why don't you do science demonstrations if you don't? I mean, what are the pressures that make it hard to get it done sometimes? Time? Yeah. Sometimes it can almost feel like a waste of time.
It takes your time and it takes the last time.
Exactly. And especially if it's something that is a little bit involved, like building this density column here. That's taxing on the person's patience because you got to dribble stuff in there. I'll talk more about it later, but there's a time commitment involved in some of this stuff. I don't know that I can give you an answer to fix that problem for you. It's going to take some preparation. But I would say too, that's probably one of the biggest reasons that I will skip an experiment if I do. It's just because I don't have time, or I'm not putting the time ahead of time to really prepare. The student, I'm teaching a blended classroom where we've got a lot of the high school students especially are pretty much individualized because we don't have big enough classes to have classes for a lot of stuff. And so especially in those cases where they'll come up on an experiment and I often don't even really know what's coming up, and that's an indictment on me, but then I'll have to quickly look over it and say, well, do we have the stuff for it, and is this something we can do here, and does it make sense for us to do it? And then I'm also often trying to weigh that. Is the value of the time going to be worth the explanation that it gives? And frankly, sometimes it's not. It depends on your science curriculum. You know, I come across, especially in middle grade science, sometimes the demonstrations they want students to spend time doing really are, I don't know, I don't think they're really worth the time. And so that's where you have to, as a teacher, you have to make that call. Yeah, time's a big deal. Preparation kind of goes along with that. I mentioned already that sometimes just having materials is an issue, especially for smaller schools. I tried to, pretty much what I've got here on the table is stuff that you probably have on hand already. That was kind of part of my title here is practical. I wanted this to just demonstrate some stuff that I think is really cool that can be done easily with stuff you have on hand. A lot of science demos will take stuff you probably don't have on hand. It will require a little bit of a budget for buying some science supplies, especially as you get into upper grades. But that's something that, again, if you plan ahead a little bit, you can kind of figure out what's coming and know what to have on. I had came across, we were supposed to break down some styrofoam recently, and so I had to run to, this is my first time in my life I entered a beauty supply store, because they have pure acetone, and it's about the only place in town that has pure acetone that I know of. So it's used as a nail polish remover. Acetone, that's kind of cool. I didn't bring that along, but take a stack of styrofoam cups and just dump some acetone on it. It just melts. Kind of cool. And they have high-powered peroxide too, if you need to make some like good reactions, elephant toothpaste and that kind of thing. The beauty supply store has you covered there too. Yeah, higher-powered peroxide than you can get at Walmart. All right. Any other comments about why do you tend not to do science experiments if you don't? Okay. Any comments about why you should? Or why you do? Or what you enjoy about it?
They end up retaining a lot more than if I would have just lectured for 30 minutes.
Right. That's true too.
How much of it sticks.
Retention is a big deal.
That's what I remember in school about science, is the times we did something hands-on or experiments.
Exactly.
It gets more excited. So science.
Yeah.
Sometimes I think science is kind of a drag, but
Yeah.
kind of break it up into some experiments here and there. It's kind of cool, actually.
Yeah, exactly. Well, and I mean, I see that on the students' faces sometimes when I call them up for science class and they come up to the table and I've got some stuff sitting there. And there's a different level of excitement for the class than if they're just coming up to, I call them up to the table, we have a little class on the back of their desk, and if it's just the books, it can be pretty boring, you know.
Somebody has said that science is actually about doing something.
Yes.
About practicing. And the analogy I heard that I stuck in my head was learning to ride a bike. If we taught learning to ride a bike the way we often teach science,
Yes.
you would say, describe the chain and talk about the history of bikes and who invented the wheel. And if they could pass that quiz, then they know how to ride a bike.
Yeah.
Well, they
Yeah.
So actually doing something.
It's true. I mean, what is a scientist? A scientist is a person who does science, who does experiments, and so part of when we talk about the scientific process, which is not a focus of mine here really, but because I'm not showing you classically designed science experiments here necessarily as much as demonstration, but science is doing, it's experimenting. I mean, there's theoretical science and stuff too, but most of what we teach is going to be talking about doing. That being said, let's get to doing. So some of this is really me just kind of showing you stuff. I should have maybe left this off for a minute. The first thing I have on your paper there is a density column. So I made this ahead of time because it is just kind of time consuming. And I don't want to sit here for 30 minutes pouring stuff in while you're watching. Did you know, I hope you did, that liquids can float on other liquids? That's what this thing demonstrates. So this is kind of in the category of talking about density and buoyancy and how to demonstrate some of those things. And what I will say too here, backing up just a bit, I'm not going to use very complicated language. I'm kind of aiming this at sort of middle school-ish concepts here, so almost everything we talk about would have much more complicated chemical equations and stuff we could talk about. That's not really where we're going. I mentioned I'm not really a science guy, right? So I like the stuff that helps me make sense of it in logical terms. Density column. I think I listed here the things I used. So it looks better if you get closer to eye level with it. So the bottom level is honey. Next one's corn syrup. If you want to do this at home, your honey and corn syrup you can just kind of dump in because they're thick enough. Try not to get it on the sides of the jar. Dump them straight in the middle. Coming on at the column, then it gets runnier and runnier, and you'll start blending them together if you're not careful. So the next one's milk, and then dish soap. And the cloudy one here is actually water, but I had such a hard time keeping it from going through the soap and pulling milk back up. So that cloudy one is just water, and then vegetable oil, and then peroxide that I have colored blue to make it more dramatic. So, not peroxide, sorry, alcohol, rubbing alcohol. Now, you could actually add layers to this. On one website I saw that listed a bunch of stuff you could do. Added maple syrup, which is kind of expensive, so I didn't add it. It would be down in here. You can actually add some like lamp oil, kerosene type stuff, which will float on top of the alcohol, actually. You can use different colors to make it dramatic. I just think this is really neat. And to add some interest, then you can start dropping stuff in there. Maybe ask your students where do you think this is going to float, and you can see what level it will float on. And then you have opportunity here to explain some of the concepts of density and buoyancy and how the two interact. What's happening even in the layers of all the liquid here is that each of these liquids has a different density. Right? Items that are denser are going to be on the bottom. The less dense you get, the more they'll sit on top of each other. Same goes for items you drop in then. So I've got some blueberries here. So he's floating on top of the water, the bigger one. I don't know if it makes any difference or not. Okay, the bigger blueberry goes on down a little bit. Little piece of plastic straw. I don't know if you can see that very well. Yeah, between the water and the alcohol, or the oil and the alcohol. I got a little bottle lid here. I'm gonna float it like that first. That's a boat, basically, right? If I sink the boat, it sits on top of the oil. Then I've got a little metal lid here. Let's see if we try to do that as a boat, will it sit on top of the alcohol? Yep, sure will. All right, let's try to sink the boat and see where it goes. All right. I can't even see where it is from this side. It went through the water, through the soap, sitting on the milk. All right. You can do this with all kinds of stuff. You can do, I saw suggestions for like a popcorn kernel. You could do a marshmallow or a ping pong ball would float on the very top. It actually floats on lamp oil because it's air. It's mostly air, pretty much. And like I said, you can kind of get a little bit of the scientific process going here. Where do you think this is going to go? Make a hypothesis, and then let's test the hypothesis, you know.
Can we try one that now? Is metal actually lighter than honey?
Then honey?
Why is it floating?
Well,
because it's full of milk? Or because it's actually lighter than...
Right. So that is...
If it was on its side, would it go all the way to the bottom?
Probably not. Because, and that has to do with what it's full of. And so that gets to, let me throw this back up here. I don't know, some of you may need to just stand up here a little bit. That gets to this more exploration of buoyancy here. This is the last one on that list in the density buoyancy section. You know, it's kind of fascinating to think about how does a ship float? Because they're metal. They're steel. Steel doesn't usually float on water, right? It's way denser than water. If you dropped a piece of metal in the water, it would sink to the bottom in a hurry. So how do ships float? And here you have the opportunity to talk about, well, you have to take the item as a whole. Basically, whatever it's full of is considered part of the thing. So a ship is full of mostly air, and air is certainly denser than water. And so although the steel is considered part of the ship, and this, you get into complicated water displacement stuff all here too, but the simple explanation that I understand is if this thing is going to float, it's going to be because it's also full of air. So you take the whole thing. And so aluminum foil will float on water, and you can actually test and demonstrate stuff here too, by putting a load in the boat and seeing how well different designs float, that kind of thing. We can have little boat competitions, kind of fun. But now, any of you know what the density of aluminum is? I don't know the number right offhand, but it is denser than water. So it should sink. It's only slightly denser than water. It's one of the less dense metals. So crumble it up. Y'all can stand up if you need to, but it's still floating. All right. So again, kind of. Sorry, I should have put more water in here. The concept is here that it still has air in it. There's still air trapped in all those little pockets and holes. You can do what I saw online called the Archimedes squeeze, because Archimedes, is credited with developing a lot of the principles of buoyancy and stuff. So this is the Archimedes squeeze. Just squeeze this ball really hard. I've seen people online who actually used a hammer or something to beat all the air out of it. If you can squash that thing really flat, then it sinks to the bottom of the hurry. What we've done there is just removed all, or at least most, of the air from diving. So now it's pretty well pure aluminum, and aluminum's denser than water. If you took all the steel in an ocean liner and crunch steel together, it would also sink in a hurry. If you fill a steel ocean liner with water, it'll also sink in a hurry, right? Which is why a hole in the Titanic was bad news. And I think that's probably what's going on with this metal lid in here. I hadn't really thought that through very much before, but if it's sitting on the mill or wherever it is, then it's full of the item above it, just like a boat is full of air, and so it's going to sit right there. Let me move back up a little bit here to freshwater and saltwater. So this is kind of, you know that things float on saltwater. Things are more buoyant on saltwater than freshwater, right? That's because saltwater has a higher density than freshwater because of the salt dissolved in it, basically. And so the saltwater itself is more dense, which means items are going to be held up out of it a little bit more. That's the layman's way to talk about it, right? So I've got 2 cups here. One is, the red one is saltwater. The yellow one is fresh water. Oh, some index cards here somewhere. Ah, yes. Put them where they need to be. All right. So when a freshwater river runs out into the ocean, that water doesn't immediately mix. And there's several reasons for it. Temperature has a big part to play in that too, but part of it is the differing densities of salt and freshwater. Oh, and by the way here, this is also a demonstration of air pressure, which we'll talk about in a little bit. A lot of good science stuff is a combination of various concepts. All right, so what I've done here, I've got the index card in between the 2. I'm just gonna hold it in here because it might make a mess. Try to keep those 2 cups lined up as much as I can. All right. My hand's probably in the way, but can you? So like I said, the fresh water is yellow, salt water is red. Probably if we let it sit there for a while, you'd see some gradual mixing as the salt water percolates up into the fresh, right? You would have the opportunity here to really demonstrate some temperature differences too. You could probably do this very same thing with really cold, really hot water, right? Because hot water's going to rise, hot things rise generally. All right, and so then you can do the same thing. Still a little separation there as the water kind of switched places, but you see the difference in, you see how it mixes quite a bit more, right? So, again, simple demonstration there of density difference and what a difference that makes, even in something as simple as water. Water actually floats on water. If it's got some difference in density of some sort. Let me pause here just a minute, and all of these concepts would have a few more ways you could talk about them and demonstrations. Are there other things here questions you have, or ways that you've thought of to demonstrate some of these concepts, or things you've seen that are neat?
So you don't have the layer on there to show us how to?
I don't. So what I used, I think I mentioned this on here. A lot of the websites that will tell you how to do a density column will say to use a turkey baster, which is basically a huge dropper, to put everything from about water up. Gets a little tricky. And so if you use a turkey baster and then put it right down close to the level you're working with and dribble it down the side very slowly, it should pool out on top of the layer below. I didn't have a turkey baster, which is part of the problem with the cloudy water. So I used this big straw I had, and put it in there, and then carefully try to pour the water through the straw into the side. I had more or less work, mostly. A turkey baster would be better, or some sort of big dropper. But like I said, anything from about water up does just get pretty tricky. So with milk and soap, it's not that hard to use a straw or something. You just kind of run it down to the side and let it cool out.
So first and then the milk, that would.
No, so I haven't tried mixing. I mean, I think you just end up with a messy mix because they try to float, try to mix up as they go. All right. Air pressure and movement. This is something that there's some things here that I just find really fascinating. Let me. Oh boy. Too many things laying around here.
Water, paper,
Yeah.
over the plate.
So set a little wad of paper just in the mouth of the bottle and then try to blow that wad into the bottle. Well, that worked too well. It looks like it should be really easy to do. You obviously, like I said, like I showed you, accidentally demonstrated. You can do it if you I accidentally placed my stream of air in just the right place to hit the very bottom and it made a return current. But generally speaking, it's really hard to blow something as simple as a little wad of paper into this bottle. There's several things going on there. One of them is that although we live in air and we don't think about it, it is matter and it takes up space. It's a little bit of a counterintuitive notion, sort of. It's like fish in water, I guess. We don't think about the fact that we're swimming at the bottom of an ocean of air. Which I like that demonstration, or that concept too, because it helps to understand air pressure a little bit too. Most people are sort of familiar with the fact that if you dive down, even in just a pool, you can feel the pressure difference as you get down just a few feet. That's because there's more water above you pushing down on you. Well, we're at the bottom of an ocean of air, and so there's a lot of air above us pushing down on us, and pushing all around us, not just down. Which also makes sense then why you go up high on a mountain. There's a little less air above you, a little less air pressure up there. I like that explanation. We live at the bottom of an ocean of air. Now, so that's partly what's going on here. This bottle's already full. It's full of air. When I try to blow this thing in there, the air that I'm using to push it in there doesn't really have a very good place to go, because it's already full. So it also demonstrates a little bit of Bernoulli's principle, which is that, well, this is a gross oversimplification. Like most scientific concepts, the simple way to say it is actually wrong. But the gross oversimplification of Bernoulli's principle is that, how do I say it? As a fluid's flow rate increases, its pressure decreases. So what's going on here is the air in the bottle is static. It's not really moving. The air that I'm blowing is moving faster, which means it has less pressure, which is why the ball falls out. Because there's less pressure suddenly right out here than there is in here. Because there's moving air here, static air here. So that explains that. There's some other, some of the other demonstrations of Bernoulli's principle would be take a air hose or a vacuum cleaner hose on blow, and you can levitate a ping pong ball or even a bigger ball. Most of you have probably seen that. Same deal. So you've got moving air on three sides of the ball on that side. You know what I mean? Cupped around the ball, and then lower pressure, because the air is moving, it kind of keeps it sucked down. The air directly on top of the ball is not moving as much, so it kind of keeps the ball pressed down in place. You can actually use that principle to do something like spin a screwdriver in a circle. Anything that's got a circular shape can actually hover in a stream of air. Now, I just discovered that when I saw some videos of it, so you'd have to trial and error, but it evidently can be done. You can demonstrate it by, there's actually, so airplanes fly, one explanation for the reason airplanes, or the way airplanes stay aloft has to do with this. The air is moving faster over the top of the wing. It's not a complete explanation. Honestly, if you look up some articles about how airplanes generate lift, the fact is nobody actually really knows. There's some common explanations. Bernoulli's principle is one of the most common, but nobody really knows, because planes can also fly upside down, most of them, for a little while, which means that faster air should be on the bottom, which means it should be pulling toward the ground, and it doesn't work that way. So there's some other stuff going on with lift that isn't explained by Bernoulli's principle, but it's at least a demonstration for an explanation. You can blow over a piece of paper, and again, if you read the Wikipedia article, they say this isn't really Bernoulli's principle, but the concept here is kind of the same, faster moving air, right? So you get a little bit of lift there because the current of air gets kind of sucked around the curve. And then you can, things like atomizers in a spray bottle that uses a flow of air to pull something up into the flow, or a hose end sprayer for your garden. Those all work basically on this Bernoulli's principle as well. Faster moving, the water or air gets squeezed a little bit, and that creates essentially a suction that pulls the other atoms, or the other items up into the flow. All right, balloon in a bottle. Let's use this one. Yeah, that one. All right, so put a balloon inside the mouth of the bottle. Stretch it over the bottle. And blow it up. I promise I can blow up a balloon. Usually. All right. Well, you already know what's going on here, right? The bottle's full. There's no room for me to push more stuff in there because the bottle's full. Well, you see it expand a little bit just because air is slightly compressible. But the bottle already has stuff in there. Now, beforehand, I took the scissors and punched a little hole right here. I've been covering it with my thumb. See what difference that makes. All right. Again, simple demonstration of the fact air takes up space, right? And if you give that air that's in there some way to escape, then you can add more to the bottle. Now, same concept at play though, right? I've forced the air out through the hole, and then I covered the hole so no more air can get back in. So now there's more air inside the balloon than outside, and there's no reason for it to deflate. That's all you gotta do. So, I thought that was kind of neat. I just ran across this recently. Simple setup. Really good for demonstrating the air pressure, air movement, how air works. How long is this supposed to go? I was going to do, you've probably all seen the pulling an egg into a bottle with a piece of paper or something, right? I was going to try it with, let's just do it. So, glass bottle. I've got a little balloon instead of egg. Partly because Well, if it works, I like the demonstration of how the water in the balloon will actually diffuse the heat of the fire inside it and not melt the balloon through. Another thing I just saw the other night as I was preparing for this is that you can actually, there was a video of somebody that used a blowtorch on a cardboard cup, a paper cup, and boiled water in a paper cup with a blowtorch, because water will actually diffuse that heat away fast enough that it never burns a hole through the paper cup. Same thing, this is a little bit of water in here. You would think it would pop with a flame under it, but it just, the water diffuses that heat out of the way. So you know that as water, in there. There you go. You know that as air heats up, it expands, right? So as it burns, it expands, it has to go somewhere. If you notice, when it first got set on there, it bubbles a little bit because that's all the hot air rushing past it. Then it seals off the top, and it runs out of oxygen. The flame runs out of oxygen, and as it quickly cools, then it pulls it in. So it actually pushes it in. So, terminology thing here. We think of this as suction, but really what's happening is this ocean of air that we live in is simply pushing it in, because there's more pressure out here than there is in there. So, you can do the same thing with handle in the bottle. This is just water. I colored it to make it more dramatic. It bubbles a little bit when you first set it there, and some of that is the heated air escaping around the rim of the bottle. Handle goes out. Oh, styrofoam plate's a bad idea, I guess. There we go. Okay, don't use styrofoam next time. It created too much of a seal. It's, as that candle goes, the same thing, same principle here. So as the candle burns out, it uses up all the oxygen, forces some of it, uses up the oxygen, turns it into CO2 and other things which are slightly more dense, so that alone creates just a little bit of pressure difference. And then as the candle goes out, the air starts cooling down quickly, and it pulls that water in while it's split. You can get a hard-boiled egg through it. It's got to be hard-boiled, but you can get a hard-boiled egg. Did I not say that? Yeah. You can get a hard-boiled egg into a container that's much smaller than the egg. So, I was gonna crush a can. I think I'll do that yet. I've got a little bit of water in this aluminum can. Same concept here. As the water heats up, it basically fills the can with water vapor and hot air. Mostly water vapor, really. And then see what happens. I'll show you what happens. You've probably seen this already.
You have a wireless burner?
It would help to plug it in, wouldn't it?
Picture it'll wait too long.
Right.
We just did that because we could see.
Right.
I'm
Good.
curious if you can use that tong because how do I handle this?
Yeah. Use the tongs or like a baking glove or something. Yeah. That could maybe work. I've seen it done, videos of people doing it with just like big heavy insulated gloves. There's a little bit of water in there. I put just a little bit of water in. I'll let it boil some. Let's move on down the list as this talks, or as it heats. Dew and frost. I don't think I'll spend time on that. This is pretty straightforward. Get a metal can, just put some water in it. If you use a thermometer, a big glass ball thermometer, to stir it as you're adding ice, you can actually tell. So start adding ice to it in small amounts. Keep stirring, and watch for when dew shows up, condensation shows up on the outside. At the point where that condensation starts happening, that is the dew point right now, based on the air pressure and the humidity in the air around it. Dew point varies wildly, based on pressure and humidity, but what's happening is the air immediately around the can cools to the point where it can't hold the moisture that's in the air anymore, and it condenses to the cooler surface. And then got a bunch of ice in there, then I add a bunch of salt. And as the salt interacts with the ice, salt drops the freezing temperature of ice or water, which is why you can't make ice cream without salt. And it's got to cool down below. If you don't add salt or something else, water doesn't get colder than freezing. Mostly. I mean, you can get super cool, pure water, but that's a whole different story. As you add salt, it cools that down below freezing, and you'll actually start to see frost on the outside of your can. So here you can demonstrate dew point frost, how frost forms. Interesting question to explore sometime. How can frost form like it does some mornings when the air temperature is not quite freezing? Do a little bit of digging into that sometime. I just didn't. I don't have time to tell you now, but it's kind of neat. There's a few things here that kind of blew my mind actually. Chemistry. So you can make a really good indicator solution with just red cabbage. I just bought a head of red cabbage. This is actually just a little bit of the water we got. Use some distilled water preferably. Boil the cabbage, drain off the cabbage pieces. You can use this to get there's something called anthocyanins in this red cabbage juice that interacts with acid and base molecules and turns different colors. Just like commercial indicator solution you can buy, except this is just neater. I like it better. Plus, you can make your students get a little bit of cooking practice too. I just trying to work. All right. So, vinegar, alcohol, milk. This one's just water. So this is about the color of the cabbage juice itself. It'll be blue or purple, slightly depending on. Tap water is always going to have some dissolved solids and stuff. It's not going to be purely neutral. And then this is hand soap and water, and this is bleach. So you get the range there. And if you could get some higher powered acids, it would be brighter pink, brighter red. And you can actually make your own little pH tables and then compare other things too. You know, what pH do you think this is going to turn out to be? And add some indicators and try it. And then you can do interesting stuff like kind of buffer some acids and see how they, how that changes the pH and stuff. Just be careful that you don't combine things you shouldn't. I was playing around with some of this the other day, and I had just kind of a discard bucket there on my desk, and I had some of this bleach water sitting in there, and then I had some alcohol in another container, and just wasn't thinking. I dumped the two together, and I noticed there was some weird swirly stuff going on, and a little bit of foam in there, and so I had my computer right there. I just typed in alcohol bleach reaction. Turns out I may have just made a little bit of chloroform. Chloroform is kind of disturbingly easy to make. It's just alcohol and bleach can actually create chloroform, which, as you know, might be used as an anesthetic, but it can also kill you instantly. So be careful. Don't combine things you don't know what they're going to do, and make sure you know what make sure you think about what you are combining. I was going to create some CO2. Basically, when you dump vinegar and baking soda together, that reaction creates, among other things, carbon dioxide. If you do it in a contained bottle, carbon dioxide is heavier than air, and so you can actually pour it out on a candle and watch the candle extinguish. It's kind of neat. I think it's lunchtime. I told you I'm going to be this absent-minded professor, right? Let me do this hot water, this bottle in the water yet. If y'all want to stand up, get a little closer. If you haven't seen this especially, here's your chance. So, at this point now, this bottle is full of mostly water vapor, and certainly a lot of hot air. And this is just cool, kind of room temperature water. All right. So what happened here was we just crushed the bottle using atmospheric pressure. there's a lot less pressure inside than outside, and as soon as it cools down just that little bit, it just crushes it. There's videos online of people doing this with 55-gallon drums. So go to town. All right. I think we'll just stop there. If you have questions about anything else on this paper, I've got stuff here. I can do some stuff. We can talk about it. Thank you for your attention.